Hi to everybody. Good morning. Happy Friday. And welcome to the December installment of MBF Bioscience's short form webinar series. I think for most of us, this time of year can get a little crazy. So I wanted to remind everybody to take a breath, slow down, and reflect for just a moment on the progress that you've made this year. It's easy to get caught up on the big things that happen, but I think it's important to not overlook the little things that have brought us to where we are. So with that being said, this week we'll be focusing on little things. We'll be focusing on puncta detection and the feature that we've implemented in Neurolucida 360. For those people who are doing research in vasculature, we do also have this feature in Veselucida 360. During today's webinar, I'll go over how to detect puncta in both simple and complex images, as well as the updated analyses that we provide in Neurolucida Explorer. Before I get into the details of this feature and the analyses, I'd like to remind everyone out there that the overall success of today's webinar is in part due to the questions that y'all come up with. So I thought it would be important to quickly cover how you can submit those questions. When you develop a question during the webinar, please feel free to send them in. Submitting a question is as easy as finding that Q&A button in the Zoom webinar panel, either at the top or bottom of your screen. Simply type in your question and hit enter. Forgive me if it takes a moment or two to find and answer your question as the webinar moves along. I'll do my best to try and stay on top of these as they come in. Lastly, as always, this webinar is being recorded and will be available later to view. A link will be sent in the email that you had provided. With all that being said, I think it's a good moment to switch on over to our demonstration portion. So, puncta detection is something that we're very excited to kind of share with everybody and you know, talk about how we've improved that over our year. As you can see on the screen here, this is a very simple image. We have a singular dendrite and we have a lot of signal around it. I believe it's GLUT1. So the signal around here is picking up on some puncta objects, and for us, we'd really want to identify exactly what's going on here. So the first step, you don't necessarily need to have a tree in place, but I've done this kind of pre-demonstration. I'll click the puncta button in the upper right hand of our 3D environment. I'll make that full screen so everyone can see it a little easier. But once we pick the puncta panel, you'll notice that it says to use the channel panel to pick a single channel. It's very Dr. Seuss-like, but what it's really doing is it's pointing us to the left-hand side of our 3D environment to pick a specific channel that we'd like to identify our puncta in. If I click on the red channel, we can see that it quickly isolates the dendrite that's been traced. Whereas if I pick the green channel, it will isolate all of the puncta that are available within this channel. Using this trace opacity slider on the left-hand side, I can either bring forward and make completely opaque the dendrite in place, or if I want to be able to visualize my data a little bit easier, I can slide this down until it's completely invisible. For the time being, I'm going to leave it there, but we also just want to get started. So there's 3 different settings that we're going to use for our puncta detection. The first is the detector diameter, which I can demonstrate here by clicking this Preview Seeds button. Similar to how our automatic tracing algorithm works, the way that we detect these objects is by placing a seed, and that's just an indicator for that targeting algorithm to hone in on that object. The diameter value here is 5, so as I zoom in on this grouping here, you'll notice that all of these circles share the same diameter of a 5 micron. That's it, 5 microns. By raising this larger, we're going to kind of isolate these smaller puncta and hopefully include more, or by making it smaller, we'll ignore some of the larger objects in our 3D environment. I can clear these seeds. That was just a visual demonstration. The other 2 settings here are the sensitivity and the minimum size. The sensitivity value is going to be based on not only the saturation of the staining, but how it contrasts with the background. A question has just come in about can you do this while live imaging, or is it only with a Z-stack? This is Neurolucida 360 only works with acquired images, so it could be a single plane or it could be an image stack that's been acquired, but we don't allow, or we don't have the ability to do live image analysis with Neurolucida 360. So as I was saying, the detector sensitivity, I apologize about that kind of quick jump and back and forth. The sensitivity looks at the saturation of the staining and the contrast between the foreground and background. The minimum size is in voxels. So how many 3D pixels does it take to identify something as a puncta or a punctum? So I'm going to go ahead and out of all of these puncta that are available, I'm going to click the detect all, and we'll work in a very vast and majorative detection. In just a few seconds, we should see a population of these puncta come forward. And from here, we're going to be able to work and kind of pull out more data or further push what we want to describe. So as I bring this slider back up, we'll see that our dendrite comes back into place, but it still is remaining in that red channel because it's been isolated to that channel. The nice thing about the channel panel is that once you've done a detection in that specific color channel, all of the data that's been generated there will be tied to that specific channel. This is a lot of information. If I go to Edit, Select All, and change the color, it'll really push forward and show just how many puncta have been detected. We can see that there's over 1,500 in this one channel. And you'll notice that there are some objects that aren't being detected as puncta. And again, if I leave the edit mode, that could be for a couple of different reasons. One, for the smaller guys, it could be because they're smaller than the 10 voxel limit that we've set. For these larger areas, it could be because, one, we don't have the detector sensitivity high enough, and the threshold of the saturation doesn't quite match up. So in that case, we can always boost the sensitivity. The second would be if there's something much larger in diameter than the 5 micron limit that we've set. So maybe something like this in the center here. That might be a little bit larger. So to get that detected, we might need to boost up this detector sensitivity. As I was saying, this is a lot of information to work with, and it might not necessarily all pertain to the data that we're trying to collect. So if I clear this, one way that we can kind of limit the data that's being generated is with this detect based on proximity checkbox. One of the questions that came in before the demonstration started is about colocalization. What I'm doing now is not necessarily colocalization, but more proximity testing or proximity detection. I want to know all of the puncta that are within a 5 micron distance of this dendrite. So now when I go ahead and click Detect All, we're still going to be using the same settings here, but now we've added an additional setting to limit the amount of data that's being produced. The difference here between proximity and colocalization, as I change the color to make it a little bit more apparent, the difference between proximity and colocalization is that proximity is a detection-based setting or scheme, and that's going to limit the amount of data that's being produced, as I said before. And colocalization is more of an analytical tool that we can use for describing spatial relations. So we're not doing any sort of colocalization here. We're just doing a proximity detection. Let's say that this is as we've wanted it to be. We can go ahead and click this Save and View in Neurolucida Explorer button. Since I have saved this data file before, it's going to overwrite the existing data file, and now it's going to automatically open in Neurolucida Explorer. From here, I can go directly to Analyze and Puncta, or punctum, and I can choose a quick summary and details. When I click OK, we'll get a very simple summary of all of the puncta that have been detected and a couple of averages that come about. And then we can also see some details on these individual puncta. That is a very simple and straightforward way to work with your data. If that's all you need to do, then you can consider this finished, and you can go ahead and click this current Windows button to push these two data tables over to Microsoft Excel. I'm going to go ahead and close this and start with a different image that's a little bit more complex, so we can start talking a little bit more about colocalization, automatic detections, and even some further analyses. So as we can see, this image is a lot more complex. There's a lot more signal, there's a lot more happening, and we can see that there's a lot of overlap between these channels. Once again, I'm going to go to Puncta. It's telling me to choose a channel, so I'll go ahead and select this red channel to start. The goal here with this image isn't to detect all of the puncta in the entire image, but more so to detect the cells that we're seeing. I'm going to turn off this proximity detection, and now one way to detect puncta, other than this detect all, is a simple click to detect. When I click to detect, you'll see that there's an error that comes up, and it says that we're not able to define the punctum here. This is very saturated, so I know that it does not have to do with the sensitivity value. So I'm going to go ahead and click this Preview Seeds button to try and troubleshoot what might be going on. And right away we can see that there's a major issue here with how we've defined our parameters. At a 5 micron diameter, this detection setting isn't going to even touch these cells here. So I'm going to clear these seeds, and one quick way to get I guess I'll say quick again, a quick measurement of these cells is by going to the 2D window and using our page up and page down keys to look at each individual plane that's been acquired. I'm going to look at the largest cell that I can find, which is right here. I'm going to zoom in so that everyone can see that a little bit easier. And I'm going to go, while I'm in this Trace tab in the 2D side, I'm going to go all the way to the right and choose Measure Line. Here I can click twice and get a very rapid measurement, a rough estimate of this length. So the diameter here is about 33. So I'll click OK. I'm going to go full screen again with this 3D environment. And now I'm going to go to my detector diameter and change this to, I'm going to say 40, just so everything gets captured in one space. I'm also going to raise this minimum size because now when I click Preview Seeds, we'll see that there is a Mod Podge of these diameters. They're all kind of interweaving up here because there is just so much signal in this image. So I'm going to clear the seeds once again, and I'm going to raise this minimum size up to something like 45. From here, I'm going to go ahead and click Detect All, and we'll see in just a couple of seconds how much more refined this detection will be. We do still have some puncta up here that are being detected, which is fine, but the majority of our detection is happening exactly where we want it to be. The next thing I can do to further refine this search, right now we have 70 puncta detected in this channel. I'm going to clear it one more time, except this time I'm going to work with our machine learning that's implemented already in the program for us. The machine learning has been trained in-house, so we are going to start looking for these more cell-shaped puncta rather than the smaller ones because we're sticking closer to our detection settings. So with machine learning, I'm going to click Detect All once more, and we should see a much more refined detection being done. One of the questions that came in to our chat is about the minimum size being based on microns rather than voxels. Unfortunately, this is just that's the only setting that we have is for voxels. We're not doing that in microns yet. Right here, we can see that we have limited the detection from 70 down to 44, which is great. And for visualization purposes, I'm going to go to Edit, select all, and I'm going to change these to a white color. Now I can go to the green channel, and you'll see that we do have very similar cells in place. And I'm going to make these white, previously detected puncta ghosts or shadows of themselves. Again, I'll keep these same parameters, and I'll click Detect All, and we should see the depiction here. I'm going to go ahead, edit, select all, and change them to a purple color that will be easily seen. And from here, we can go back and look at all of the channels together once again, and we can see all of these cells that have been properly created and defined. I'm going to go ahead and click this Save and View button one more time. This time, since I haven't saved it, I'm going to save this as colocalized puncta. Once we've done the save function, it's going to go into Neurolucida Explorer, and we can start looking at the puncta that have been defined here. I'm going to pause for just a second and look over at some of these questions, and hopefully I can answer them. So please forgive the moment of silence. Espen is asking, does the detector diameter mean minimum, maximum, or just approximate? That's going to be, so if I return back for a quick second, when we're doing this detection, let me pick the channel. When I preview seeds, it's going to be a little bit hectic once again, so I apologize for that. What it's doing is we're looking from the center or centroid of that puncta, and we're drawing a straight line out to create that diameter. So that's going to be the maximum detector diameter for the settings there. If there are objects that are larger, we can always increase this and do a click to detect to get those individual objects detected. But it is a maximum, not a minimum. You guys are amazing. A lot of these questions are just rolling in, so I appreciate that. I'm going to bounce back to Neurolucida Explorer just to do something very quick, and then I'm gonna work through with some of those questions that are still coming in. So here we are, Neurolucida Explorer. We have all of our puncta that we've detected. So what I'm going to do now is I'm going to choose all of the punctum in my Trace Structures tab. I'm going to go to Analyze, Punctum, and again, I'll do a quick summary and details. And then this is where we can start to look at some of the colocalization that's happening. By clicking on the colocalization summary, we can set our own threshold of what we want that overlap or the colocalization percentage to be. In this instance, I'm going to choose 50%. And when I click OK, you'll see that the results are almost instantaneous. Again, we do have our simple results like the averages and the details. We do parse that out into the different channels, which is very nice. And then over here, we have a pretty basic colocalization result. For 50% of that overlap, we have 22 puncta in channel 2 that overlap with channel 1. We can return to punctum, and we can choose 100% to see exactly how many are completely overlapping, and there's only 6. So there's different ways that we can kind of get the data pulled out from our data file to get these reports generated. And the nice thing here is that we do allow you as the user to define what your colocalization percentage is and how you want that to be kind of written out. I'm going to pause here for just a moment. I'm going to close this down. I'll just leave this up for now. I'm going to look through these questions that are coming in. Aria had a question that she sent in a while ago, so I apologize about that delay. Compare fluorescence luminance strengths of spines in one channel. Is the Puncta tool the one I need? What's the difference between this and the contour feature? Great question. So if you're looking at luminance strengthened spines, I would assume that you would probably want to use the spine detection. The Puncta tool could be helpful, but that's really only if your Puncta is in a different channel from your branch. I don't know if I'm answering this directly or if it's kind of a windy turny answer, but you should be able to use that spine detection to get a more accurate depiction of the spine rather than the Puncta tool. And the difference between this and the contour feature, it's a lot less manual. If you're drawing contours around things, we're not going to really be able to generate those volume and distance measurements as much as we are here. It's going to result in you doing a lot more manual labor as opposed to having the program try and run through and do those detections for you. A couple of questions have come in about machine learning. The machine learning, we have a classifier that has been trained in-house here at MBF Bioscience. At this moment, we don't have a way for y'all to train your own classifiers and do that on your own, but that is something that we can always talk about in the future or kind of offline. We're always kind of looking to advance our machine learning algorithms and figure out a way of how it can best suit your data. So I would say if you're trying the machine learning now, see how it works for you. If it's great, keep using it. If it needs a little bit more fine tuning or you think it might need a little bit more training, please feel free to reach out to our technical support department. They're going to be more than happy to help kind of point you in the right direction and see how we can improve those detections for you. We have just a couple more minutes here, so I'm going to just pull back a little bit more so that I can show some of the results that we've worked on over the past year, some of these analyses. So I'm going to, once again, close Neurolucida Explorer. I'm going to close the image and data files that are open here, and I'm going to bring in an entirely different set of data. This is something that started out as multi-channel image data, and we've gone ahead and made it monochromatic so that you can see everything that's going on. Because this is an already reconstructed data file, there's going to be trees, there's going to be spines, and there's going to be puncta, all of which have already been labeled. So this is a nice little cooking show demonstration for everybody. My colleague Dan Peruzzi is asking a question about machine learning for particular sizes. Machine learning can be used for any size puncta. So really what it comes down to is when you define the parameters here, the machine learning is just going to kind of add a level to that detection. So yes, it can be used for any puncta of any size. Great question, Dan. So as I mentioned, I'm in the 3D environment. I clicked on puncta. We have over 1,500 puncta. We have over 2,000 spines. And as you can see here, we have a bunch of different branches. What I'm going to do is just open this in Neurolucida Explorer. And in just a second, we should see that pop up over here. The computer is just thinking, so this is a great time to look over some of the other questions. What type of files can we import into Neurolucida 360? Can we use images taken on confocal, for example, or could we convert to TIFF and import? Both are completely applicable. We can read an abundance of files. I can show the kind of file spec or what we can read, but the available formats are pretty vast. OIF is certainly available, and if you run into an issue with that, converting to TIFF is always easy enough. We do also, I'll put a plug out there, we do also have our own free converter, so if that's something that you're interested in, please feel free to visit the website. It's called Microfile Plus, and it is, as I said, a free not program converter, it is a free file converter. So we can convert your image series into a 3D stack. We can convert 3D stacks into other 3D stacks. And then we can also do multi-channel series. There's a bunch of different ways that we can convert. We can also use our favorite JPX format. or OME TIFF format to be converted into? So that's a fantastic question. So the reason I was so excited to talk about this data structure is because not only do we have axons from multiple cells, we have dendrites, we have spines, and we have puncta. If I go, I'm just going to make it a little bit simpler for everybody. I've gone through and I've selected a couple of different branches that do have puncta and do have spines involved. So rather than throwing up a massive amount of data, we're just going to focus on this little cluster in the center here. I'll go to Analyze, Punctum, and this time I want to show off something a little different. With this colocalization availability, this analysis, we're going to keep it at 50%, but two things that we've added since our last Puncta webinar are these details analyses. So we now have colocalization details and distance from additional structure details. When I click OK, let me shrink this down so it all fits on one screen. The reason that this is so exciting is because not only are we going to do colocalization with puncta, we're going to be doing colocalization with your branches, with your spines, with your somas, your varicosities, anything that you've generated data-wise in Neurolucida 360, we can now start to look at the overlap in colocalization. So here, with these two branch structures, we can see that there are 7 puncta in the original channel 1 data and 26 that have aligned with spines. So 7 with dendrites, 26 with spines, and that's just a 50% overlap. To break that down even further, we can see exactly which tree is identified as having a 50% overlap with puncta and which spines individually. And the nice thing here is that we do show the classification, whether the tree is a dendrite or an axon, and we show the classification of the spines as well. So we can see here that spine 2 has 1 puncta that is at least 50% overlapping. The nice thing about this as well is if we go and do, let me select group 3 once again. I'm going to go to Structure, Branch Structured Analysis, and Spines. When we click on Spine Details, we're going to get a bunch of information on these spines, but more importantly, we'll see that spine 2 and spine 2 in this list are the same spines. So when we do the reporting in this punctum colocalization details, we're making sure that the objects that are being labeled here will be consistent throughout the data file. The same goes for these details over here. So when we talk about distance to additional structures, we're talking about those branches. And so now we can see, since there are 7 puncta that are 50% overlapping with this dendrite, we can really see how far each puncta is away from the individual, or the individual puncta is away from the 2 dendrites. So we can really see how close, and as we click through the data table, we're seeing exactly which dendrite is being represented. So those are 2 additional analyses that we've added based on customer requests and feedback. We know that you guys are always pushing the boundaries of science and really giving us a lot to work with on the development side. So that's always greatly appreciated. Are the puncta analyses available through the Neurolucida 360 system as well? We do have the ability to generate puncta. The analyses are in Neurolucida 3 Explore are essentially the same. We're still working on getting these detail analyses up and running in that program, but you should be able to do the exact same processing and creation of data in Neurolucida 360. So thank you for that question, Katie. If you're looking at the same spines at different time points, can their identity be preserved at different time points? Thomas, thank you for asking that as well. Actually, I think I'm doing a demonstration for you in a couple upcoming weeks, so I look forward to that. But we do have a program particularly, it's called microdynamics, and that is used for in vitro imaging or kind of the time point imaging that we're used to. So if you do have, I can see you're excited about it as well. If you do have different time points you're working with, microdynamics does preserve that information. And with that repeated imaging process, it's going to keep track of those time points automatically for you so that you can identify changes over time to those dendritic spines. So I would point you in the direction of microdynamics if that's what you're looking for particularly. But for just details on spines, this is going to be a fantastic tool to get you started. We're running close to the time limit. We're a little bit over actually, but I appreciate everybody asking all these questions. This is amazing. I'm just going to hopefully go for this last one here from Claudia before I end things here. But the question is about puncta detection using the center of mass. I'm asking to know if it could be detected something like a ring. That is a fantastic question. So the question, I'll read it out loud with a little bit of a language change. If there's no staining in the center, but there is in the cell membrane, so if you're just getting a sort of ring, will puncta detection be able to pick that up? It's going to be a little bit difficult, but I think as long as the edges are saturated, I don't want to promise that you'll be able to get the full detection. I think you should be able to get it. You may have to increase the detector sensitivity and make sure that whatever your detector diameter is truly encompasses the whole kind of mass. But I believe you should be able to do that. If not, there are always filters that we can apply, and in this case, I would probably try to focus a little bit more on maybe the closing filter, but that would probably be the best way to do the detection that you're looking for if the detection as it is doesn't necessarily work for you. With all that being said, I want to thank Francisco Alvarez and Sarah Stanley for their permission to use the data files and image stacks that I had shown. So thank you. And then I also want to thank all of you for joining, for asking your questions. This was amazing. This is a great way to end the 2021 year. And hopefully we can start off 2022 with a bang with another short form webinar. Please feel free to reach out to the info at MBF Bioscience if you're looking for more information on NL360, on any of our products. And please feel free to fill out the short survey. I'd love to get your opinions, your ideas on upcoming topics that you'd like to see. But truly, this has been a pleasure. I appreciate everybody for attending and for listening, and for all the questions that you've asked. Enjoy the upcoming weekend, and I look forward to talking to you all soon. Thank you, and take care. Bye, everybody.